You flip a switch. Light floods the room. Simple, instant. But inside that LED bulb, something impossible is happening. Electrons are vanishing and reappearing. They are tunneling through barriers they should never cross. They are behaving like particles and waves simultaneously. The light you see is not just electricity converted to brightness. It is a direct window into quantum mechanics, the strangest rulebook in the universe. Every photon streaming from that diode carries proof that reality at the smallest scale operates nothing like the world you see. So why does quantum mechanics run your LED? What makes these bulbs fundamentally different from every other light source? And why did it take scientists decades to understand what was actually happening inside them? Particles are particles, waves are waves. But experiments over the next 3 years prove him right. In 1927, Clinton Davison and Lester Germer at Bell Labs fire electrons at a nickel crystal and watch them diffract like light. Waves passing through a slit. That same year, George Paget Thomson at Cambridge scatters electrons through thin films and sees concentric rings, interference patterns impossible for particles. The electron has wave-particle duality. It is both, always. Werner Heisenberg publishes his uncertainty principle in 1929. You cannot know both the position and momentum of an electron at the same time. The more precisely you measure one, the more uncertain the other becomes. This is not about measurement limits. This is fundamental to reality. An electron does not have a definite position and momentum. The math is simple, but the implications shatter classical physics. Delta x times delta p is greater than or equal to h divided by 4 pi. Planck's constant divided by 4 pi. That constant, 6.626 times 10 to the negative 34 joule seconds, is tiny, which is why you never notice this in everyday life. But at the scale of an electron in a semiconductor, it dominates everything. These materials have a band gap, an energy chasm between the valence band where electrons sit at rest and the conduction band where they can move freely. In silicon, that gap is 1.1 electron volts. An electron needs that much energy to jump across. Once it does, it leaves behind a hole, a positively charged absence that behaves like a particle itself. When an electron in the conduction band meets a hole in the valence band, they recombine. The electron drops back down. Energy must go somewhere. In silicon, that energy becomes heat. Phonons, lattice vibrations, no light. Silicon is an indirect bandgap material. The electron and hole have different momentum values at their energy levels. To conserve both energy and momentum during recombination, the electron must also create or absorb a phonon. That makes photon emission extremely unlikely. This is why your computer chips do not glow. Gallium phosphide, gallium nitride, these are direct bandgap materials. The electron and hole have matching momentum at the band edges, no phonon required. When they recombine, the energy can release as a photon with no extra steps. The wavelength of that photon depends entirely on the bandgap energy. E equals h times f. Energy equals Planck's constant times frequency. Frequency and wavelength are related by the speed of light. So wavelength in nanometers equals 1,240 divided by band gap in electron volts. Gallium arsenide has a band gap of 1.4 electron volts. Wavelength 900 nanometers, near infrared, invisible. To get visible red light at 650 nanometers, you need 1.9 electron volts. Mix gallium arsenide with gallium phosphide. The alloy shifts the band gap. Engineers discovered this in the 1960s. Nick Holonyak at General Electric made the first visible LED in 1962 using gallium arsenide phosphide, red light. 2 years later, he moved to the University of Illinois and continued development. By the 1970s, you could buy red LEDs commercially, traffic lights, calculator displays, indicator lamps. You need a band gap around 2.7 electron volts for blue light at 460 nanometers. No suitable material existed. Researchers tried silicon carbide in the 1920s, but the output was weak and the manufacturing terrible. Then, in the 1980s, Japanese scientists tackled gallium nitride. Isamu Akasaki at Nagoya University, Hiroshi Amano, his student, Shuji Nakamura at Nichia Corporation. Growing high-quality gallium nitride crystals was brutal. The material wants to form defects, impurities, crystal dislocations. These defects create non-radiative recombination centers where electrons and holes combine without releasing photons. Wasted energy, low efficiency. In 1986, Akasaki and Amano developed a method using a buffer layer of aluminum nitride on sapphire substrates. This reduced defects significantly, but they still could not dope it p-type effectively. P-type doping adds holes. You need both n-type with electrons and p-type with holes to make a diode junction. Doping. The magnesium atoms were there, but electrically inactive. The electron beam freed them. First, blue LED. 1993. Nakamura, working independently at Nikkei, found that thermal annealing in nitrogen atmosphere does the same thing. Simpler, scalable. He optimized the growth process using metal-organic chemical vapor deposition. High brightness blue LEDs hit the market in the mid-90s. Nakamura, Akasaki, and Amano shared the Nobel Prize in Physics in 2014. The citation said, "Their invention enables bright and energy-saving white light sources." True, but that is just the surface. The quantum mechanics underneath is far stranger. If you value documented semiconductor physics and quantum optics history like this, subscribe. It is the best way to support our work. Also comment from which city you are hearing this from. This script is researched and factual, using sources from the Engineering Libre texts published September 8, 2022 on electron-hole recombination mechanisms, and light-emitting diode physics on Wikipedia updated October 6, 2025 on bandgap materials and device structure. Now back to the information. The negative terminal connects to the N-type side. Electrons in the N-type region get pushed toward the junction. Holes in the P-type region get pushed toward the junction from the other side. They meet in the depletion region, a thin zone at the interface between the two semiconductor types. This zone is typically 10 to 100 nanometers wide. At that scale, quantum effects dominate. An electron approaching from the N side does not have a definite position. It is described by a wave function, a probability distribution spread across space. Heisenberg's uncertainty principle guarantees this. If the electron is confined to a small region, its momentum becomes highly uncertain. That means it has a range of possible velocities. Some parts of its wave function extend into the p-type region even before it officially crosses the junction. This is quantum tunneling. If the ball does not have enough energy to reach the top, it rolls back down. Always. But electrons are not balls, they are waves, probability waves. The wave function does not stop at the barrier. It decays exponentially inside the barrier but does not vanish. On the other side, there's a small but non-zero probability of finding the electron. The transmission probability depends on the barrier height and width and the particle mass. Thinner barriers mean higher transmission, lighter particles mean higher transmission. Electrons are light, barriers in semiconductors are nanometer scale. Tunneling happens constantly. In standard LEDs, tunneling is a minor effect. But in some advanced designs, researchers deliberately use it. Resonant tunneling diodes, unipolar doped bipolar tunneling structures. A team led by Changchun Institute of Optics in China reported in Applied Physics Letters, August 2000s. 16 in Light Science and Applications, 2017, that they created LEDs using only N-type doping. No P-type layer. They inject electrons normally. But they inject holes by Zener tunneling across the gallium nitride bandgap into the valence band. High electric fields make the barrier thin enough that electrons can tunnel directly across the gap from the conduction band to create holes on the other side. This avoids the resistive P-type contacts that plague conventional gallium nitride LEDs. Phys.org covered this November 17th, 2017, noting these tunnel LEDs could provide more light with less voltage and resistance than conventional designs. When they meet, their wave functions overlap. The electron drops from the conduction band to fill the hole in the valence band. This is electron-hole recombination. In a direct bandgap material like gallium nitride or indium gallium nitride, the electron and hole have the same momentum. Energy must be conserved. Momentum must be conserved. A photon carries almost no momentum compared to an electron, but it carries significant energy, so the electron can drop and emit a photon directly. This is radiative recombination. The photon energy equals the bandgap energy. E equals hc divided by lambda. Energy equals Planck's constant times the speed of light divided by wavelength. Flip that around and wavelength equals 1240 divided by bandgap in electron volts. Gallium nitride has a bandgap around 3.4 electron volts. That gives ultraviolet light at 365 nanometers. To get blue light at 450 nanometers, you need about 2.75 electron volts. So manufacturers use indium gallium nitride. Adding indium narrows the bandgap. Indium 20%, gallium 80% nitride gives you blue. More indium gives you green at 520 nanometers. Less indium gives you violet. But not every recombination produces a photon. This is the problem. You can have non-radiative recombination, 3 types: Shockley-Read-Hall recombination, Auger recombination, surface recombination. Shockley-Read-Hall happens when defects in the crystal create energy levels inside the bandgap. Think of them as stepping stones. An electron drops partway down into a trap state, then drops again to the valence band. Each step can release energy as heat instead of light. William Shockley and William Read published the theory in Physical Review, September 1st, 1952. The recombination rate depends linearly on carrier concentration. At low current, this dominates. Auger recombination involves three particles. An electron and hole recombine, but instead of emitting a photon, the energy transfers to a third carrier, another electron or another hole. That carrier jumps to a higher energy level, then gradually releases the energy as heat through phonons. Auger recombination depends on the cube of carrier concentration. At high current, it dominates. This causes the infamous efficiency droop in LEDs. As you increase current past a certain point, efficiency drops. Your LED gets brighter, but not proportionally. A paper in Applied Physics. Letters in Nature, Light Science, and Applications. November 30th, 2023 from the US. Department of Energy Office of Science describes work by Emmanuel Kiopakis and Chris van der Walle showing Auger recombination is the culprit in nitride LEDs. They use computational simulations, running on 4,000 processor cores for a total of 1 million processor core hours. They calculated from first principles the interactions of charge carriers under different conditions. The results confirmed Auger recombination, but also uncovered indirect Auger processes involving carrier scattering. Imperfections in the gallium nitride crystal lattice and thermal vibrations cause electrons to bounce around irregularly. These disorganized collisions create recombinations that produce electrons or holes instead of photons. The energy dissipates as heat. The effects of indirect Auger recombination were found to be about 1,000 times stronger than direct Auger. Processes. Van der Walle stated, with Auger recombination now established as the culprit, we can focus on creative approaches to suppress or circumvent this loss mechanism. Surface recombination happens at the edges where the semiconductor crystal terminates. Dangling bonds, incomplete lattice structure. These create trap states. Electrons recombine non-radiatively. To minimize this, manufacturers passivate surfaces with thin layers of other materials, aluminum oxide, silicon dioxide. This fills the dangling bonds and reduces trap density, but you cannot eliminate it entirely. Every LED loses some energy to non-radiative recombination. The internal quantum efficiency is the fraction of electron-hole pairs that produce photons. For modern blue LEDs, this can reach 80 to 90% at moderate currents. But at high currents, Auger recombination cuts it down. This is why your LED bulb runs cool. Most of the waste energy is not heat from resistance. It is energy lost in non-radiative recombination inside the semiconductor junction itself. Now consider what happens to the photon after it is emitted. The electron drops from the conduction band to the valence band in about 1 nanosecond. The photon is born with energy equal to the band gap. It starts moving in a random direction. But it is inside a semiconductor with a high refractive index. Gallium nitride has a refractive index around 2.4. Air has a refractive index of 1. When light tries to exit from a high refractive index material to air, it can reflect back. Total internal reflection. The critical angle is about 25 degrees from perpendicular. Any photon approaching the surface at a steeper angle bounces back. It rattles around inside the chip. Eventually, it might hit an impurity and get absorbed, lost, or it might find a path out. But the light extraction efficiency of a bare flat semiconductor chip is only about 4%. This is terrible. Most of the photons you work so hard to create never escape. To fix this, manufacturers shape the chips. Pyramids, cones, rough surfaces. This changes the angles and lets more photons escape. They also encapsulate the chip in a plastic dome with a refractive index between gallium nitride and air. This reduces the reflection. Modern high-efficiency LEDs achieve light extraction of 60 to 70%. Combine that with internal quantum efficiency of 80%, and you get overall external quantum efficiency around 50%. 50% of the electrical power in becomes light power out. That is far better than an incandescent bulb at 5% or a fluorescent at 20%. When the electron drops and emits a photon, the emission is spontaneous. The electron does not decide when to emit. The timing is probabilistic, governed by quantum mechanics. The rate of spontaneous emission depends on the density of electromagnetic modes available at that energy. This is the Purcell effect, named after Edward Purcell, who described it in 1946. If you place an emitter inside a cavity that resonates at the photon frequency, the emission rate increases. If you place it in a photonic crystal that blocks that frequency, the emission rate decreases. The vacuum is not empty. Even empty space has quantum fluctuations, virtual photons constantly appearing and disappearing. These fluctuations interact with the electron. You can think of spontaneous emission as stimulated emission caused by vacuum fluctuations. This view comes from quantum electrodynamics. a paper published in AIP Advances, January 22, 2020, by Raul Martín Palma, titled Quantum Tunneling in Low-Dimensional Semiconductors Mediated by Virtual Photons, proposes that tunneling itself can be understood as electron-hole annihilation and creation involving virtual photons. The electron does not pass through the barrier continuously. Instead, it annihilates on one side, creating a virtual photon, which then creates an electron on the other side. This framework resolves the paradox of a particle with energy lower than the barrier height passing through. The particle never actually is inside the barrier in a classical sense. It is a quantum transition mediated by the electromagnetic field. A paper in Physical Review Letters. October 1st, 2025, by Jagang Park and Professor Bumki Min from KAIST. Korea Advanced Institute of Science and Technology showed that spontaneous emission behaves contrary to previous predictions. Infotonic time crystals. These are materials whose refractive index oscillates rapidly in time. Earlier theory predicted the spontaneous emission decay rate would vanish at a specific frequency. But the KAIST team proved the decay rate is actually significantly enhanced. They also predicted a new phenomenon called spontaneous emission excitation, where an atom gains energy and transitions from ground state to excited state without absorbing. A photon. This work fundamentally shifts the paradigm of spontaneous emission research. Another study from Stony Brook University, led by Dominic Schnebel, published in Nature Physics, November 18, 2024, in Physical Review. Research. August 21st. 2024 demonstrated control over spontaneous emission using ultra-cold matter waves instead of photons. They built arrays of microscopic atom traps that emit matter waves and observed collective emission. Effects where multiple emitters synchronize. They achieved subradiant states where spontaneous emission is suppressed and observed where the radiation hides in the array. These discoveries show that even after 100 years, quantum emission is still revealing surprises. It hits a rod or cone cell in your retina. The photon is absorbed by a molecule of rhodopsin or photopsin. That molecule changes shape. A cascade of chemical reactions begins. A nerve impulse fires. Your brain interprets it as light. The photon no longer exists. Its energy has been transferred. It fulfilled its quantum mechanical destiny, carrying energy from the electron's drop across the band gap in the semiconductor to a chemical reaction in your eye. The chain of events is quantum from start to finish. The electron is a probability wave, the tunneling through barriers, the recombination governed by wave function overlap, the spontaneous emission triggered by vacuum fluctuations, the photon as a discrete energy packet. Even the absorption in your eye is quantized, one photon, one molecular reaction. Classical physics cannot describe any of this. Every step requires quantum mechanics. Different band gaps give different wavelengths. Aluminum, gallium, indium phosphide for red, orange, yellow. Indium, gallium nitride for blue, green. But you also see white LEDs everywhere, light bulbs, flashlights, phone screens. White is not a single wavelength. It is a mixture. There are two ways to make white LEDs. Method 1, combine red, green, and blue LEDs in one package. Vary the current through each. You can produce any color in the visible spectrum. This is how RGB LED strips work. Method 2, use a blue LED and coat it with a phosphor that absorbs blue light and emits yellow light. Blue plus yellow looks white to the human eye. Most white LED bulbs use this method. The phosphor is usually cerium-doped yttrium aluminum garnet. YG:(Ce). Blue photons from the LED hit the phosphor. Electrons in the cerium ions absorb the photon energy and jump to higher energy levels. Then they drop back down in multiple steps, releasing photons across a broad spectrum centered in the yellow. Some blue light passes through unconverted. The combination of blue and yellow produces white light with a correlated color temperature around 3000 to 6000 Kelvin, depending on the phosphor thickness. The color rendering index, a measure of how accurately colors appear under the light, can reach 80 to 95 for good white LEDs. This is excellent, but the phosphor adds another layer of quantum mechanics. The cerium ions in the YAG crystal have their own electronic structure. The absorption and emission involve quantum transitions between 4f and 5d orbitals. The crystal field from the surrounding aluminum and oxygen atoms splits the energy levels. This determines the exact wavelengths absorbed and emitted. Solid-state physicists have spent decades optimizing phosphor chemistry to get the right color balance and efficiency. A quantum dot is a nanocrystal of semiconductor material so small that quantum confinement dominates, typically 2 to 10 nanometers diameter. At that size, the electrons are confined in all three spatial dimensions. The allowed energy levels become discrete, like an atom, rather than continuous bands. The band gap depends on the dot size. Smaller dots have larger band gaps and emit shorter wavelengths. Larger dots have smaller band gaps and emit longer wavelengths. You can tune the emission color precisely by controlling dot size. Cadmium selenide quantum dots emit green to red. Cadmium telluride dots emit red to infrared. Lead sulfide dots emit infrared, but cadmium is toxic, so researchers developed alternative materials. Indium phosphide, perovskite, nanocrystals, carbon dots. A paper in Nature Light, Science and Applications. August 19, 2025 reports electrically pumped amplified spontaneous emission from colloidal quantum dots. The team developed a top-emitting cavity with silver and indium zinc oxide electrodes that eliminated surface plasmon losses and confined the optical field within the quantum dots. This increased gain twofold. They achieved quantum dot light-emitting diodes with high optical gain and high current injection. This is a step toward quantum dot lasers driven directly by electricity. Earlier quantum dot LEDs required optical pumping with another light source. Phys.org reported July 9, 2024 on quantum dot emitters that generate entangled photon pairs for quantum computing. The team at Niels Bohr Institute fabricated a photonic crystal waveguide that provided strong confinement. Coupling efficiency exceeded 90%. Per cell enhancement reached 16, meaning the spontaneous emission rate was 16 times faster than in free space. The emitted photon pairs violated the Bell inequality, confirming they were genuinely entangled. These are no longer just light sources, they are quantum information devices. LEDs do not heat up the way incandescent bulbs do. An incandescent bulb works by running electric current through a thin tungsten filament until it glows white hot at 3000 Kelvin. Most of the energy radiates as infrared. Only about 5% becomes visible light. The rest is wasted heat. A fluorescent bulb uses an electric discharge through mercury vapor to generate ultraviolet light, which then excites a phosphor coating on the tube. Efficiency around 20%, but an LED operates near room temperature. The semiconductor junction itself runs warm but not hot. The chip might reach 60 to 80 degrees Celsius under high current, but that is nothing compared to an incandescent filament. The reason is quantum mechanical. Energy is released as photons during radiative recombination, not as bulk heating of the material. Yes, non-radiative recombination produces heat. And yes, electrical resistance in the contacts and wires produces some heat. But the fundamental energy conversion mechanism is photon emission, which does not require high temperature. This makes LEDs far more efficient. 50% electrical to optical conversion is common. The best lab devices exceed 70%. Atoms get closer together. Valence electrons experience stronger electrostatic interactions. The potential energy increases. This increases the band gap. For gallium nitride, the band gap increases by about 0.06 millielectron volts per Kelvin as temperature decreases. A group of physics teachers discovered this by accident. A high school teacher on a website called The Physics Well describes an experiment done in his classroom. He cooled a green LED in liquid nitrogen at negative 196 degrees Celsius. He expected the LED to shift toward longer wavelengths, red shift. Instead, it shifted toward shorter wavelengths, blue shift. The peak emission wavelength moved from 571 nanometers at room temperature to a shorter wavelength in Nikola-S-OM. The liquid nitrogen, spectroscopy confirmed it. The color shifted from green-yellow toward blue-green. The explanation is that lowering the temperature increases the band gap due to lattice contraction. Larger band gap means higher photon energy, means shorter wavelength. This effect is well documented in the literature, but counterintuitive. Most processes slow down at low temperature, but the band gap itself is not about kinetic energy of atoms. It is about the quantum mechanical spacing of allowed electron energy levels, which depends on atomic spacing. Tighter lattice, higher band gap, blue shift. Multiple quantum wells, quantum wires, quantum dots. A quantum well is a thin layer of narrow bandgap semiconductor sandwiched between layers of wide bandgap semiconductor. For example, indium gallium nitride, a few nanometers thick between gallium nitride layers. Electrons and holes are confined in the narrow layer. This confinement quantizes their energy levels perpendicular to the layers. The allowed energies form discrete steps. The emission wavelength depends on the well thickness. Thinner wells give shorter wavelengths. Modern high brightness LEDs use multiple quantum wells, 5 to 10 layers of indium gallium nitride separated by gallium nitride barriers. This increases the volume where recombination happens and boosts light output. The quantum confinement also modifies the density of states. More electron-hole pairs can exist at the same energy, leading to higher radiative recombination rates. A paper in Science Direct. February 16th, 2021, on effect of quantum barrier width and quantum resonant tunneling in indium. 20% gallium, 80% nitride parabolic quantum. Well structures analyzed how barrier width affects LED efficiency. They modeled resonant tunneling diode structures that exhibit negative differential resistance, a region where increasing voltage decreases current. This property is crucial for LED operation. Thinner barriers allow more tunneling, higher current, higher light output. But there is a trade-off. If barriers are too thin, carriers can tunnel out of the well before recombining. This reduces efficiency. The optimal barrier width is around 10 to 15 nanometers for indium gallium nitride wells. If you measure a quantum system frequently enough, you can freeze it in its current state. The active measurement collapses the wave function. If you collapse it repeatedly, the system never has time to evolve. In LEDs, this manifests subtly. Interactions with the environment, phonons, other charge carriers, defects, act as continuous weak measurements. This can suppress certain quantum transitions and enhance others. Recent theoretical work suggests that controlling these interactions could improve LED efficiency by steering carriers away from non-radiative pathways. But this remains speculative. The engineering challenges are enormous. One more quantum phenomenon shows up in LEDs, shot noise. Light consists of discrete photons. The emission times are random, governed by quantum mechanics. If the average emission rate is n photons per second, the standard deviation in counting is the square root of n. This is Poisson statistics, purely quantum. Shot noise sets the ultimate limit on measuring light intensity. Let me bring this back to the original question. Why is LED light quantum? Because every part of the process requires quantum mechanics. Electrons behave as probability waves. They have wave-particle duality. They obey the uncertainty principle. They tunnel through barriers. They recombine with holes by overlapping wave functions. The photon emission is spontaneous, governed by quantum fluctuation of the electromagnetic field. The photon energy is quantized, determined by the band gap. The photon itself is a discrete particle of light. It travels as a wave, but interacts as a particle. It can be absorbed only in whole units, never fractions. The color depends on the semiconductor band structure, which is pure quantum mechanics. The efficiency depends on competing quantum processes, radiative versus non-radiative recombination. The temperature dependence reflects quantum mechanical changes in the lattice and energy levels. The confinement in quantum wells creates discrete energy states. Even the statistical fluctuations in the light output are quantum in origin. There is no classical explanation for any of this. You cannot build an LED with classical physics. It would not work. You need quantum mechanics at every step. You need a direct bandgap semiconductor with a bandgap around 2.75 electron volts. Very few materials qualify. Gallium nitride works, but growing high-quality crystals is hard. The lattice constant does not match common substrates like silicon or sapphire. This creates strain and defects, dislocations, impurities. These defects trap carriers and cause non-radiative recombination. In the early attempts, gallium nitride LEDs were dim and inefficient. It took decades of material science to solve these problems, developing buffer layers, optimizing growth conditions, finding ways to activate p-type doping. These are engineering challenges informed by quantum physics, but not solved by quantum theory alone. The theory told you what you needed. The practice required grinding through thousands of experiments. Akasaki, Amano, and Nakamura spent years on this. Their success transformed the lighting industry. Today, LED production exceeds billions of units per year. They consume less energy than any previous light source. They last longer. They are smaller. They enable technologies impossible with older bulbs. High-resolution displays, solid-state lighting, Wi-Fi communication using modulated LED light to transmit data, optogenetics using LED light to control neurons in living brains. All of this rests on quantum mechanics. This script is researched and factual using sources from the Wikipedia article on light-emitting diode physics, updated October 6th, 2025, covering band-gap materials and emission mechanisms, and from the US. Department of Energy Office of Science report published November 30th, 2023 on Augur, recombination and carrier scattering in nitride LEDs with computational simulations performed by Kiyopakis and Vandawala using 1 million processor core hours. Now back to the information. This bridges two realms, the quantum world and the everyday world. Most quantum effects are hidden. You do not see electrons as waves, you do not observe superposition, you do not watch particles tunnel through barriers. But an LED makes quantum mechanics visible, literally. The light you see is direct evidence of quantum processes. Every photon is a quantum. The wavelength is determined by quantized energy levels. The randomness of emission events reflects quantum probability. When you flip a switch and the LED turns on, you are commanding electrons to perform quantum mechanical transitions, trillions of them per second. Each one a little miracle of quantum physics, each one demonstrating that the universe at its deepest level runs on rules that defy common sense. Two photons created simultaneously from the same recombination event can be entangled. Their polarization states are correlated. Measure one, and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance. It bothered him deeply, but experiments confirm it is real. The Bell inequality violations prove it. Quantum entanglement is now used for quantum cryptography and quantum computing. An LED, a simple light bulb, can be a source of entangled photons. The boundary between everyday technology and quantum information science is dissolving. The Nature Physics paper, July 9, 2024, showed quantum dot LEDs generating photon pairs that violated the Bell inequality with ultra-low pump power. The per-cell enhancement of 16 boosted the emission rate. Coupling efficiency over 90% meant nearly all the emitted photons were collected. This opens the door to scalable quantum communication networks. Imagine fiber optic links secured by quantum encryption where the photons come from modified LED chips. No expensive lasers, no cryogenic cooling, just engineered quantum dots in a diode. Spontaneous emission is irreversible. An excited electron drops and emits a photon. The photon escapes. You cannot reverse this process by simply running time backward. The photon does not come back and re-excite the electron. This seems to violate time reversal symmetry, which is supposed to hold for fundamental quantum processes. The resolution lies in the environment. The photon escapes into the vast electromagnetic vacuum with essentially infinite modes. The probability of the reverse process, a photon with exactly the right energy and phase coming back and hitting the electron, is effectively zero. This is quantum decoherence. The system loses its quantum coherence due to interaction with a large environment. The wave function collapses. Information leaks out. The process becomes irreversible even though the underlying quantum mechanics is time reversible. Spontaneous emission in an LED is a prime example of this. The electron drops, the photon leaves, entropy increases, time moves forward, the arrow of time emerges from quantum mechanics plus environment. No two electrons can occupy the same quantum state. This is why semiconductors have band structures. Electrons fill the valence band states. The conduction band is mostly empty. When you inject electrons into the conduction band, they settle into available states. When you inject holes, removing electrons, you create empty states. Recombination happens because an electron finds an empty state and drops down. If all valence states were full, recombination could not happen. Pauli exclusion is essential. The International Energy Agency estimates that LED lighting reduced global electricity consumption for lighting by several hundred terawatt hours per year by 2020. That is multiple large nuclear power plants worth. Carbon emissions reduced, costs reduced. LEDs last 25,000 to 50,000 hours versus 1,000 for incandescent. Maintenance costs plummet. The Nobel Committee noted in 2014 that 1/4 of global electricity consumption goes to lighting. LEDs are changing that. Auger recombination at high current density limits brightness per unit area. This is why high-power LED lamps use arrays of many small chips. High-quality gallium nitride wafers are expensive. Manufacturing requires sophisticated equipment. Nevertheless, LED prices have plummeted. A 60-watt equivalent LED bulb that cost $50 in 2008 costs less than $5 in 2025. Volume production drives cost down. Beyond lighting, LEDs enable displays. Every smartphone screen is an array of tiny LEDs behind filters or self-emissive quantum dots. The image you see is millions of pixels each controlled individually. Vary the current, and you vary the brightness. Combine red, green, blue, and you get any color. All running on quantum mechanics. Scale it down, repeat it millions of times. Add control electronics. You have a display. Flow cytometry, optogenetics, DNA sequencing machines. In optogenetics, researchers genetically engineer neurons to express light-sensitive proteins. Shine blue or yellow light on the neurons, and you can activate or silence them. LEDs deliver the light via optical fibers implanted in the brain. The quantum transition in the LED drives the quantum transition in the channel rhodopsin, which opens ion channels, which changes the neuron's voltage. Quantum mechanics all the way down. Researchers are exploring using LEDs as single photon sources. If you drive a quantum dot LED with very short electrical pulses, you can get it to emit one photon at a time on demand. This requires quantum dots, small enough that only one electron-hole pair exists at a time. When that pair recombines, it emits one photon. This is deterministic single photon emission. useful for quantum key distribution and quantum computing. A Nature paper. August 19, 2025, describes progress on electrically driven quantum dot LEDs with high emission rates. The challenge is eliminating multiphoton events and ensuring indistinguishable photons. Progress is steady, but silicon has an indirect bandgap, so it cannot emit light efficiently. Solution: integrate gallium arsenide or indium phosphide LEDs onto silicon chips. This enables optical data transmission at terabit per second speeds with lower power than copper wires. Data centers already use silicon photonics. Future CPUs might use it for intercore communication. Military and aerospace applications benefit too. LEDs replace incandescent bulbs in aircraft cockpits and submarines. Weight savings matter. An LED fixture weighs less. Reliability is higher. No fragile filaments. Mars rovers use LED lighting. The Curiosity rover and Perseverance rover both use LEDs to illuminate work areas. In space, every watt matters. LEDs maximize efficiency, and the quantum mechanics that make LEDs work operates the same way on Mars as on Earth. One last thought experiment. Imagine a single photon emitted from an LED. Follow it. The electron in the gallium nitride conduction band wave function overlaps with a whole wave function in the valence band. Recombination occurs. The quantum state collapses. A photon is created with energy 2.75 electron volts, wavelength 450 nanometers blue. It propagates through the semiconductor, hits the shaped surface, refracts through the encapsulant, exits. Into air travels at 300 million meters per second, crosses the room, enters your eye, refracts through the cornea, passes through the aqueous humor, through the pupil, through the lens, through the vitreous, humor hits. The retina absorbs into a cone cell in the fovea, changes. The conformation of a photosyn molecule triggers a cascade of reactions, hyperpolarizes. The cell sends a signal through the optic nerve to the visual cortex in the back of your brain. Interpret it as blue. All of that from one quantum event. One electron, one hole, one photon. Multiply by trillions per second, and you have steady blue light. The aggregation of quantum events produces the classical experience, but the foundation is quantum, irreducibly, fundamentally, unavoidably. Wave-particle duality is not optional. The uncertainty principle is not optional. Quantum tunneling is not optional. Wave function collapse is not optional. Photon quantization is not optional. The Pauli exclusion principle is not optional. Spontaneous emission now driven by vacuum fluctuations is not optional. These are not approximations. They are the reality. The LED is a quantum device. The light it produces is quantum light. When you flip the switch, you are invoking the deepest laws of physics. You are harnessing the strange rules that govern the subatomic world and making them work for you. You are converting electrical energy into photons using the quantum mechanical properties of semiconductors, engineered at the nanometer scale. You are witnessing quantum mechanics in action, visibly, reliably, every single day. And here is the reveal that reframes everything. In 2025, the United Nations declared it the International Year of Quantum Science and Technology, marking 100 years since the formalization of quantum mechanics in 1925 with Heisenberg's matrix mechanics and Schrödinger's wave equation. UNESCO coordinates global events. The resolution notes that quantum engineering is leading to more energy-efficient and affordable solar cells and low-emission LED light sources. The LED is not just a product, it is proof. Proof that quantum mechanics is not abstract theory confined to textbooks and laboratories. It is the operating system of the universe. Every photon from every LED in every device you own is a small but undeniable demonstration that the world is quantum. The switch on the wall is a portal. When you flip it, you're not just turning on a light. You are summoning the uncertainty principle, the wave-particle duality, the Pauli exclusion principle, the band theory of solids, the quantum mechanical density of states. The radiative transition rates the photon as a discrete excitation of the electromagnetic field. You are making the invisible visible. You are turning quantum mechanics into light.